Hello and welcome. In today's lesson, we will talk about integration by parts. Now, integration by parts is a powerful technique used in calculus to evaluate integrals where the integrand is a product of two functions. The method involves breaking down the integrand into two parts, one part which we differentiate and the other part which we integrate in order to simplify the original integral. So this technique is particularly useful when dealing with functions whose integral cannot be obtained using the standard methods such as trigonometric, logarithmic, or exponential functions. Now, the integration by parts formula is usually derived from the product rule of differentiation, and it can be expressed in several forms depending on the specific functions that we wish to integrate. The technique requires careful selection of which part to integrate and which part to differentiate based on the particular strategy or set of rules. So the method is an important tool for solving a wide range of mathematical problems, which includes those in physics, engineering, and finance. And it is often used in conjunction with other integration techniques such as substitution, partial fractions, and trigonometric substitutions to tackle more complex integrals. The mastery of the integration by parts requires practice and experience, as well as a solid understanding of calculus concepts and techniques. So we shall consider a function y, which is defined as u times v, a product of two functions. If a function is defined as a product of two functions, then it is possible to differentiate this. If u and v are functions of x, then we can differentiate this using the product rule of differentiation as follows. So note that if our function is defined as y is equals to u times v, then the derivative dy by dx is expressed as u dv by dx plus v du by dx. This statement here is what we call the product rule of differentiation, basically used to differentiate functions which are products of two functions. Now, suppose now we integrate both sides of this expression using suppose that we integrate both sides of this expression with respect to x, so that on the left-hand side we have the integral of dy dx with respect to x. On the right-hand side we have the integral of u dv by dx plus v du by dx, and we integrate this with respect to x. You notice that the right-hand side, or rather the left-hand side, dx here cancels out, and we are left with the integral of dy, which we can write is the same as the integral of u dv by dx. We integrate this with respect to x plus the integral of v du by dx. Again, we integrate this with respect to x, so that this one reduces to the integral of dy, which is equals to the integral of u dv plus the integral of v du. Integration of the right-hand side will give us y, which will be equals to the integral of u dv plus the integral of v du. But remember that y was u times v. Y was u times v. That's how we had defined our y. So if we substitute this one back here, then we shall have u times v is equals to the integral of u dv plus the integral of v du. So we want to transpose this expression and make one of the quantities here, particularly the integral of v u dv, the first term on the right hand side, we make it the subject. So it involves just moving one of this term to the other side, so that you have u times v minus the integral of v du is equals to the integral of u dv. Or even we can write this in a better way. The integral of u dv is equals to u times v minus the integral of v du. Now this expression is now what we call the integration by parts. This is what we call integration by parts. So it involves now integral of a function where the integrand can be expressed as a product u and dv. So it means that once we choose our u and dv, we'll need to integrate dv to get v, and we need to differentiate u to get du here. So basically, as we had said before, the method involves carefully selecting the function, one of the function to differentiate and the other function to integrate. And then we substitute in this formula. So this formula is what we call integration by parts. Integration by parts. So here we have y is equals to u times v. So we have the product rule. Then from the integration of that, we get the formula that we call integration by parts. Now, the method is useful when we want to integrate functions, integrals that contains functions like x to power n multiplying f of x, where f of x is an exponential or a trigonometric function, or where the function f of x is a logarithmic or inverse trigonometric function, or where we have the product of a trigonometric and an exponential function. Now, the success of the method depends on the proper choice of the function u to differentiate and the function dv to integrate. So, for you to succeed in using this method, you need to carefully select this function. Now, a simple rule that can be used to assign these functions is known as the LIATE rule. This is an acronym that stands for logarithmic, inverse, algebraic, trigonometric, exponential. So we are thinking of a function logarithmic, a logarithm of some function x, inverse, like the tan inverse of x, for example. An algebraic is x raised to power n. Trigonometric can be cosine or sine function. Then the exponential e raised to power ax. The inverse can be the inverse tangent, inverse sine of some function, the inverse cosine, and so on. So this acronym, L stands for logarithmic, I for the inverse trigonometric function, A for the algebraic, x raised to power n, T for the trigonometric function, and E for the exponential function. So given any integral of the form listed above here, 1, 2, or 3, the function that occurs first in the acronym is assigned to u, and the other one is assigned to dv. So for example, if you have an integral like the integral of x squared plus 5 times logarithm of 3x, so we see that here we have two functions. This one is a product of two functions, x squared plus 5 and logarithm of 3x. Now, x squared plus 5 is an algebraic function, while the other one is a logarithmic function. So we have algebraic, which is x squared plus 5, and then logarithmic, which is logarithm of 3x. Looking at our acronym, we check which one occurs first, A or L. We say L is the first one, logarithmic. A comes later, meaning that we are going to assign u to the logarithmic function. So we assign u to be logarithm of 3x. Now the rest becomes now dv. Once we assign this one to u, the other one, which is x squared plus 5 dx, becomes dv. So here we note that L occurs before A in the acronym, and therefore we set u to be logarithm of 3x and dv, the other function. So suppose that we have, again, a similar expression, but this time we replace the logarithm with the cosine. So we'll see that we still have a product. The first one being, one of the function being x squared plus 5, which is an algebraic function. The other one is the cosine function. A cosine is a trigonometric. So we have x squared plus 5. This one is algebraic. We have cosine of 3x. This one is trigonometric. Now we check which one occurs first in our acronym, A or T. So we see that starting from here, A comes before T, which means that we are going to assign u to the function x squared plus 5. This time, we assign u to be x squared plus 5, and then dv becomes the other function, cosine of 3x dx. Notice the reason why we have done that, because A occurs before T. It is A that comes first, then T. So since the algebraic comes before trigonometric in our acronym, then the function u is x squared plus 5. Let's look at an example. For example, we have this. We have seen that in this particular case, we have the functions x squared plus 5, which is an algebraic function, and we have logarithm of 3x, which is a logarithmic function. Then we check our acronym. We see that L comes before the algebraic A, meaning that the function L here, the function logarithm of 3x, is assigned to be u. U is equals to logarithm of 3x. So logarithm of 3x is equals to u. That is the function now we differentiate. So differentiation of this, differentiating u with respect to x, we get 1 over x. Then we make du the subject. So du becomes 1 over x dx. Then dv is now the other function, x squared plus 5 dx. Now we integrate to get v. The integral of x squared plus 5 becomes 1 over 3 x cubed plus 5x. At this point, we don't add the arbitrary constant of integration. Note that. We don't add the arbitrary constant of integration at this point. So we substitute in the formula. The formula says the integral of u dv is equals to u times v minus the integral of v du. So our integral was this. So we get u times v. We have the function u here, which is 3x, times v, which is this one. Then minus the integral of v du. V is 1 over 3x cubed plus 5x. And du is 1 over x times dx. So we substitute. We simplify this. we say that this one can be simplified because we can divide each term here by x to get x squared and 5 here. So we have 1 over 3 x cubed plus 5x logarithm of x, that's the first term, logarithm of 3x, sorry, minus the integral of 1 over 3 x squared plus 5. Now this one is a simple integral. It's in the standard form. So we can now integrate x squared to get x cubed over 3 and multiply by a third to get 1 over 9 x cubed. Then the integral of 5 is 5x. And at this point now we add the arbitrary constant of integration. We have a second example. We have the integral of 2x minus 1 cosine of x. So here we notice that the integrand here is a product of two functions. One of them is 2x minus 1. This one is an algebraic function. The other one is cosine of x. This one is a trigonometric function. We look at our acronym, LIATE. We check which one occurs first, A or T. We notice that A occurs before T, and therefore we choose U to be 2x minus 1. Then dv becomes the other function, cosine of x dx. So we are going to differentiate u and integrate dv to get v. So we set u to be 2x minus 1 and dv to be cosine of x dx. The derivative of u with respect to x will be 2, so that du becomes, otherwise we have du by dx is equals to 2, so that du becomes this one becomes 2 dx, not dx over 2. So we have let me do it here. We have the integral of 2x minus 1 cosine of x dx. So u is chosen as 2x minus 1. Du by dx becomes 2. And from here we get du is equals to 2 dx. Then dv is equals to cosine of x dx. So v will be the integral of dv, which is the integral of cosine of x dx. Integration of the cosine function will give us the sine of x. And now we have the integral of u dv is equals to u times v minus the integral of v du. So that the integral of 2x minus 1 cosine of x dx becomes, we have u, which is 2x minus 1, times v, which is sine of x, as we have seen here. Then minus the integral of v, which is sine of x, then du, which is 2 dx. So we get, this is 2x minus 1 multiplying sine of x, then minus 2 integral of sine of x with respect to x. Integration of sine of x will give us negative cosine of x, so that the solution becomes 2x minus 1 sine x, then plus 2 cosine of x plus a constant. At this point, we now add the arbitrary constant of integration. At that point, we add the arbitrary constant of integration. So basically, in this case, Once we have this integral, we start by noting that we have the function 2x minus 1 in cosine of x, and this one is an algebraic function, or this one is a trigonometric function. Then we check our acronym, LIATE. We notice that a comes before t, and so u is assigned the function 2x minus 1. Then we differentiate that. And then we integrate the other function, which is the cosine function. So that's the solution. We have another one here. The integral of 3x plus 2 multiplying e raised to power 5x. And we can work out the same way. We have the integral of 3x plus 2 e raised to power 5x. We integrate with respect to x. We note that there are two functions, 3x plus 2. This one is an algebraic function. And then we have the e raised to power 5x. This one is an exponential function, e. Then we check. We want to find out which one comes first, a or e in our acronym. A comes before e, meaning that u is said to be 3x plus 2, and dv is equals to e raised to power 5x dx. So du is obtained by differentiating. Du by dx is equals to 3, and therefore du becomes 3 dx. On the other hand, here v is obtained by integration of dv. So we integrate e raised to power 5x with respect to x, and this becomes 1 over 5 e raised to power 5x. And again, as we said, we don't add the arbitrary constant of integration at that point. And now we have the formula. The integral of u dv is equals to u times v minus the integral of v du. So we have the integral of 3x plus 2 e raised to power 5x dx becoming u times v. U is 3x plus 2, and v is 1 over 5 e raised to power 5x. Then minus the integral of v, which is 1 over 5 e raised to power 5x, times du, which is 3 dx. So that we get this is equals to 1 over 5, 3x plus 2 e raised to power 5x, then minus 3 over 5, the integral of e raised to power 5x, and we integrate with respect to x, which will give us 1 over 5 multiplying 3x plus 2 times e raised to power 5x. Then integration here will give us 3 over 25 e raised to power 5x. Then at this point we add the arbitrary constant of integration. So we see that the method is easy to apply, but what is important is to ensure that you choose the functions u and dv carefully. The function should be carefully chosen to ensure that you have the right function. You have the right function. We can apply the method for a definite integral the same way, only that now we will have the limits of integration. So here we have x squared plus 1. This one is an algebraic function, and we have logarithm of x. This one is a logarithmic function, L. So when you check in the acronym, you'll notice that L comes before A. So U is chosen to be the logarithm. So U is chosen to be the logarithm, then dv, the other function, the algebraic function. You integrate dv to get v, you differentiate u to get du. Then you substitute. The only difference here is that we have the limits of integration. The method is worked out the same way. The problem is the steps are the same, only that now here we have the limit, so we end up with a value and not a function. So basically, this is the method that we call integration by parts.